Alright, Chapter 6, Ionic and Molecular Compounds, Section 6.1, Ions, Transfer of Electrons. So in Chapter 5, we saw where the electrons were placed. We learned about electron configuration, orbital notation, valence electrons, and then we also learned about atomic size, atomic radius, and ionization energy. Now some of those things are brought up again, so it's important that you understand that material. Go back and rewatch the videos, ask questions if you have questions. But we're gonna move on here. So most elements that are found in nature, they're not found as elements. They're actually found as compounds, and we're using the word compound loosely here. But why? Why are they found as compounds? Well, as it turns out, elements form compounds to become more stable. Generally, in science, when we say more stable, what we really mean is lower energy. Okay, so when elements combine to make a compound, they typically do that in order to lower their energy, which makes them more stable. Alright, now be careful with this next little part here. It says to form a compound, elements will lose, gain, or share electrons to acquire 8 valence electrons. Now, what's special about that? Well, 8 valence electrons is that S2p6 configuration, which is a full valence orbital. So it's actually better to say that elements will lose, gain, or share electrons to have a full valence orbital, S2p6. Now, this has been called the octet rule, but you never want to cite the octet rule as a reason why. What you want to cite is a stable electron configuration by having a full valence orbital, S2p6. We'll talk about two types of chemical bonds, ionic and covalent bonds. And now it's important to note here, a bond is a very, very strong force of attraction. We'll talk about other weaker forces of attraction later, but now we're just talking about very, very strong forces of attraction. We're going to start out by talking about ionic bonds, and in an ionic bond, we have a transfer of valence electrons. So it goes from the metal to a nonmetal. Let's investigate that idea of a metal to a nonmetal. To a new page here. All right. So this is going to be a metal versus nonmetal. Okay. Let me grab. I got this periodic table here. Let me grab this real quick. Alright, and this is just to remind you. So let's say we have something like sodium. Okay, sodium's a metal, right? Anything to the left of this is a metal, for the most part. So sodium's a metal. So let's grab sodium, okay? So here's, let's say that's the sodium nucleus, okay? And then let's have it combined with its typical guy that it combines with that most people talk about, and that is chlorine. So here's chlorine. Okay, now, what's the size of sodium compared to chlorine? Pause. Get your answer. Well, sodium is a large atom. So I'm going to draw sodium about like this. Right? Compared to chlorine, sodium is large. Chlorine is small. So here's chlorine. Okay? Now, let's talk about Coulomb's law. Coulomb's law says that there's a force of attraction here. And that force of attraction depends upon the charges, Q1 and Q2. Well, in this case, we're talking about the nucleus and the other atom's electron. So we're talking about the force of attraction between these two, and the force of attraction between this nucleus and the sodium's electron. So we're talking about this force of attraction, okay? So Q1 and Q2 here are basically the same, all right? Now, what's different? The distance between the two is what's different, right? So chlorine, look at how close chlorine's protons are to sodium's electrons. That's a strong force of attraction right there. Then look at this. that is a weak force of attraction, relatively speaking. So remember what the note said. The note said metals tend to lose electrons to nonmetals. Why? Well, because the nonmetal has a stronger force of attraction for the metal's electrons than vice versa, and that's why. So why does the nonmetal gain the electron? Stronger force of attraction. Why does it have a stronger force of attraction? Because it has a smaller atomic radius. Why does it have a smaller atomic radius? Because it has a stronger nuclear force. The protons are effectively stronger. Okay? So, we've already sort of brought back up this chapter 5 material. So we're going to be talking about ionic bonds in this video. In a subsequent video, a couple sections away, we'll talk about covalent bonds. Covalent bonds, we are sharing electrons, all right? And I'll talk about the size of the atom when we get into that. All right, now, when atoms lose or gain electrons, they are no longer atoms. They become an ion, all right? So an ion is any charged particle. All right? So let's look at a positively charged particle, and we're going to become positive when we lose electrons. Remember, electrons are negative. Okay? So take a look here. Sodium normally has 11 protons. It normally has 11 electrons. That's when it's an atom. But here we're going to lose 1 electron, right? And so we end up with a positive 1 charge. Okay, and just to sort of show you, it's got 11 positives, 10 negatives. We end up with a positive 1 charge. So take a look at what happens though. All right, and let's talk about this. So here's sodium, right? Here's the nucleus, 11 protons, 11 electrons. Here's the outermost electron. Why does it lose the outermost electron? Because it has the weakest force of attraction between the nucleus and that outermost electron. That's why it loses the outermost and not one of the inside ones. But look what happens to the size. So the ion compared to the atom, it gets smaller, right? So the cation, which is a positive ion, we'll get that here in a second, is smaller in size than the atom. Why? Well, right here. Now there are 11 protons that are pulling on 10 electrons. So those 11 protons are effectively stronger, pulling those electrons in even closer. Now we've also lost that valence electron, which was the outermost. So let me draw you a Bohr model of sodium here. So here are the 11 protons, right? Let's periodic table. It's 3s1. Okay. So there's 1s2, 2 electrons, 2s2, 2p6, and then here's the 1 valence electron that's going to lose, 3s1. Okay? So when I lose that electron, goes off. Right? What do we lose? We lose the outermost energy level. So now, by default, the electrons are closer, but they're even closer than they should be because of the extra protons, and we'll see that here in a second. So here's a magnesium ion. Notice the name. I don't really change the name of the metal, I just say ion. So magnesium ion is a positive 2 cation. It's got 12 protons. It loses 2 electrons to become 2 positive. Okay. And you can see here, there's original electron configuration. Look at its new electron configuration. The outermost S and P is now full. Which, remember, outermost S and P full means it's stable. So a positively charged ion is called a cation. You always write the number first. So it's like magnesium 2 positive. It's not magnesium positive 2. As we said, the cation is smaller than the atom it came from. Why? Because the atom loses its valence electrons. And so now a lower energy level with 8 valence electrons is now on the outside. But we also want to say, and the nucleus, i.e. protons, nucleus is effectively stronger. Alright? So to name the cation is just the name of the metal and then you add ion. So it's sodium ion, it's magnesium ion, it's silver ion, zinc ion, aluminum ion. You get the idea. Alright, let's talk about nonmetals. Nonmetals gain valence electrons in order to have a full outermost s and p orbital. And we already sort of looked at why they gain electrons over here, right? We said that they're small, right? And so their nucleus is really close to the other atom's valence electron, as long as it's a metal, right? So that's what we sort of talked about. Ooh. So now these nonmetals are gaining electrons, so now they are negatively charged, right? We're gaining something that's negative, so we're negatively charged. So here's an example. We've got chlorine with 17 protons, 18 electrons, so that's an extra negative, so we're a 1 negative charge. Take a look what happens to the size of the ion. Take a second and see if you can explain that, of why the ion is bigger. So let's write this down here. The anion, which is what the negative ion is called, is greater than the atom it came from as far as size. So the reason why, take a look. We have 17 protons, 18 electrons. Now what that means is that we have the same number of protons, extra electrons. So the nucleus is effectively weaker. Alright, sorry, we're back. So what I was saying is that because now we have 17 protons, right? 17 protons. Now we have extra electrons. So the nucleus can't hold the electrons in as close, which makes the ion get bigger than the atom it came from. But here again, you can see the electron configuration goes from 3s23p5 to 3s23p6. It is that full, stable electron configuration. Alright, so we call a negative ion an anion. People always mispronounce it an anion. It's an anion. Again, you know the symbol, the number comes before the charge. The anion is bigger than the atom it came from. Why? The atom gains valence electrons, and the added electrons, we have electron-electron repulsion, and a weaker force of attraction from the proton. So again, this idea of Coulomb's law. Now, important part. The metals, we didn't change the name. Nonmetals, we changed the name. We change it to end in IDE. So let's look at some examples. So all of these over here, all of these ions are lithium ion, sodium ion, potassium ion, yada, yada, yada. But then over here, This is nitrogen, but we call it nitride. Phosphorus, phosphide. Oxygen, oxide. So we changed the ending of the name to IDE. Now that's for a monatomic ion. And you may ask yourself, what's a monatomic ion? Well, it's a single atom that's an ion. I know, how can an atom be an ion? But that's just what it is. So, for instance, oxygen is the single atom. Now that's compared to what's called a polyatomic ion, which we'll learn about in this chapter, which is something like SO4 2 negative. Okay, so this is a group of atoms that have a charge. What we're talking about is a single atom that has a charge. All right? So these atoms will lose or gain a predictable number of electrons. Okay? So generally, whatever it takes to have that stable electron configuration. Remember, large atoms lose electrons, small atoms gain electrons, and it's all because of Coulomb's law, Coulomb's force of attraction. Now they do that in order to have that stable electron configuration. So let's look at a periodic table here real quick. All right? Let me blow this thing up. There we go. So let's look at lithium. Just do lithium as an example. All right? Lithium has 3 electrons. It has 1 electron in that valence shell, right? Because it is 1s2, 2s1. So if it could lose that 1, now it has a full outer orbital. And that's stable, right? So lithium is going to lose 1 electron to lithium. What do you think sodium is going to do? Well, we've already talked about it. But it has that 3s1. If it lost that, now, take a look. It has 10 valence electrons, which means that it has a full s and p orbital. We'll see that same trend all the way down. So all of these group 1s will always form a positive 1 charge. Now we don't typically write the 1s because that positive is a 1 charge. Right? Beryllium. Look at what beryllium will do. Beryllium is 1s2, 2s2, which is somewhat stable, but not as stable as 1s2. So beryllium will actually lose 2 electrons. Same thing with magnesium, with calcium, with strontium. So it'll actually form a 2 positive charge. Now, interesting thing here, boron, right here, which is 1s2, 2s2, 2p1, boron will actually have a somewhat stable structure to form 2s2, which is kind of neat. Okay, we'll get into that later. But let's talk about the things that you need to know. Group 1, positive 1. Group 2, positive 2. Just aluminum, positive 3. And then there's only 2 more that you have to really memorize. Zinc is positive 2. Silver is positive 1. So it goes 3, 2, 1. Right? Now again, these lose 1 electron to have this stable configuration. These lose 2 electrons, 1, 2, again to have the stable configuration. Now let's go over here. Let's talk about the anions. The group 17 is going to gain 1 electron. So it's going to be 1 negative. That's over there. Oxygen group is going to be 2 negative. Right? So it goes down to tellurium. This 1 negative goes down to astatine. Now, nitrogen group is going to be 3 negative. And that's really only nitrogen and phosphorus. We don't really see arsenic participating like that. And that's it. Those are the ones that you have to have memorized for right now. So group 1 is positive 1, group 2 is positive 2, aluminum is 3, zinc is 2, silver is 1. Then over here, group 17, negative 1, group 16, negative 2, group 15, negative 3.